Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about world's largest solar thermal dish. So let's dive deep into it. So what exactly we are talking about? We are talking about this puppy. Now this puppy has 380 meters basically, and these meters are kind of special. They have sandwich layer between 1 mm thin glass that is acting as a mirror and a stainless steel sheet, GI sheet behind it, and then more glass and more sheet. So basically these are strong enough that you can walk on it, even though it's a glass. So awesome glass, and total weight is around 26 ton. So it's a big puppy. Now, the surface area that it has, that it can act on, so to say, is 500 meters square. That's why it's world's largest. The second largest is around 490, something like that. So it's not the world's largest by a very huge margin, but it is damn close. And it has dual axis tracking, meaning it's gonna make a serious eye contact with sun, and it can survive that. And what about the X multiplication? Basically, how much surface area is being concentrated to what area? So you are looking at around 500 meter square concentrated to 600 millimeter square. So that is 830x in terms of area concentration. That is huge. Means we are talking about some serious temperature here. Now this is in Vadodara, Gujarat, India, hot place in India basically, and this is in Australia. This is the second largest. So this is the dish that we are specifically talking about because this dish is well suited for hot places. So what is the output of this puppy? Output is 500 degrees Celsius steam at 50 bars. Now be mindful that bars can be increased. If you are in a scenario where you need high pressure in terms of basically your bar rating, you can go up to using pumps and some check valves, you can go up to 160 bars. Now why do you need pumps? Well, here's the deal. Water do heat up and they do increase in pressure, but consequences, it goes everywhere. So it will come back to your water tank. So for that reason, you have to have some love, some check-off valves and continuous flow. So you need some pumping power. This system is using a 50 bar pressurizer pump. So if you need more pressure, you have to invest that into from an electrical point of view, but it will not consume too much energy because heat is taking care of most of the things. So the core focus is on high pressure and temperature steam for industrial use. They are not focusing on power generation. Can you use this sort of steam and all that jazz for power production? Yes. Should you do that? Hell no, because you will go bankrupt if you try to do that. So it's one of those things where you need high pressure steam and that's the whole point. High pressure and high temperature steam, if that's your requirement, only then this puppy makes sense. Now who needs this? Well, India's granddaddy needs it. Basically pharmaceutical industry. India is huge pharmaceutical industry. Textile, huge textile industry. Air conditioning, we really need this. My electricity bill is going bonkers because of this. Electricity, basically air conditioning. Cooking, now thankfully India has invested like around 20-30 years ago, we figured it out. We have like giant kitchens that cooks for 10,000 people per day, so they need this sort of solar help for cooking at mass. Then it also has to be planned and built specific to your need, meaning if you have a paper mill industry, you will have a different requirement. You have fabrication industry, textile industry, you will require a different kind of planning structure. It's not a control C control V technology. It's not just like, oh, I'm going to take it and I'm going to paste it, because be mindful, the pressure and temperature both are throttlable. You design it. For example, let's say some weird reason you need very let's say high pressure but low temperature steam. Let's say you just need it. You have to tailor that solar concentrator part and pump design. So it has to be done properly. It cannot be just like, hey, can you buy sell me one? They can sell you, but it's like to really milk the ROI, basically to reduce the time it takes to recoup your investment, has to go down. For that reason, it has to be done properly. It's not just, hey, bring me one. It's not like that. So this is the output of that, and its core focus is industrial steam use, so to say. Now, the company that is making this, they are claiming tri-generation. Now, you have to understand, tri-generation simply means you're getting 3 mode of work out of it. One mode is electricity, obviously. Second is cooling, which is compulsory for India. Third is heating. Now, you're like, wait a minute, you need cooling and heating at the same time? Yeah, many places you need. So let's understand the energy flow. So you have solar concentrator. What does solar concentrator add to your system? It adds bars, as in pressure. It adds temperature in terms of 500 degrees Celsius. So then the first steam thick pipe goes into back pressure turbine, this puppy basically. Now you have to understand, turbine is a pressure reducer device, meaning you look into a coal power plant, you'll be like, steam pipe is coming this small, like very high pressure, GG amount of pressure, very hot. It goes into turbine, megawatts of energy come out. But here's the deal, the steam temperature does not drop that much. Like, of course, there is some drop, but does not drop that much as you will think. If it's like 400 goes in, almost 350 will come out on the other end. You're like, wait a minute, where the heck the energy came from? Pressure. So you can have hundreds of psi going in, almost partial vacuum coming out on the other end. And yes, that's how it is. Like, partial vacuum is there. There are vacuum gauges monitoring it. So pressure drop can be achieved using turbines. Now, thankfully, we have figured this out kind of early ago that because of our geometry, engineering, metallurgy, it's better to make a furnace that is high pressure, as in like it's trying to make as high pressure steam as possible. It is far more efficient. Awesome. Problem is, most things don't need those sort of pressure. You can get like 230 degrees Celsius steam. Awesome. Super awesome for fabric industry. And then we're like, sir, we need it at 5 bars. Now your boiler is like, bro, 50 bars, man. So what do? We drop the pressure. Consequence, we are just wasting energy. So somebody figured out, hey, what if we put turbine there? Rather than just forcing it downwards, we extract energy for it to go downwards. This puppy. This is what we call back pressure turbine. So it could take in, like generally, the bigger the gap between your input and output pressure, the more energy it can work and more efficient it will be, but it will still work if you have low bar gap. For example, let's say your input is 50, you need 10 output, it will still work. It won't be amazing, but it will still work. And now, if you have 150 going in and you need, let's say, 10 output, this puppy is like, I got you back, bro. This is gonna make some serious energy. As in, like, some units are as small as like few kilowatts, some goes as big as few megawatts. Like, this is serious puppy. Hundreds of kilowatt is like a general industrial use, so to say. So you take back pressure turbine, it produces electricity. You got electricity. That's the first part of trigeneration. Second, you use vapor. I always keep confusing the name, VAM, basically absorption chiller. And this puppy requires temperature. It does not require pressure, requires temperature. So instead of wasting the pressure part, you are like, hey, I use the pressure part, now take care of the heat part. This removes heat. It uses that heat to do work, basically to do the cooling. So now you have your cooling, you have reduced majority of your pressure, you have reduced majority of your temperature, but this puppy is still hot. You had hundreds of degrees Celsius when it got in. So it's not going to be like the output coming out of here won't be like, let's say, it won't even be close to 50 degrees Celsius. Most likely would be 70 to 80 or even 100 degrees Celsius. So at that point in time, you use it for low heat cases. For example, laundry case. The location that we are talking about, they were focusing about, they have a hospital near to them. So that hospital requires insane amount of laundry. Obviously, all hospitals need that. They need to sterilize that, obviously. And that consumes a lot of power because it requires steam. What if you're like, steam? Free. Trigeneration. You are using heating, you are using cooling, you are using electricity. Now this puppy, if done correctly, if the system is designed properly, you should reach a point where all the auxiliary power requirement of the solar dish, of the this system, all the ecosystem, this puppy should produce more than that. Not by a lot. Do not expect, like, let's say your auxiliary power requirement is 10 kilowatt, they should give you like, let's say 15 kilowatt. So you will only get like 5 kilowatts of extra, but it should remove your auxiliary to zero. Like your auxiliary power requirement, this puppy should be like, I got this. And this has been done with other plants also. So it's not a new concept, has been done, but it's a very weird place where you need cooling and heating at the same time. So that's why it's not so popular or well known, but it's a doable thing. So then we come to the storage aspect of it, because this is solar, it works, it's India, it's hot, it works. Now here's the problem, generation may not line up with the demand time. For example, when your consumption is, for example, the steam from this puppy is used for cooking breakfast. Now here's the breakfast happens early in the morning. This will not come to full power unless it's like, bit later than that. So what do? Do you wait? No, that defeats the purpose of breakfast. So what they have figured out is like storage will be a perfect solution here. Now the storage here is not designed for basically overnight storage kind of scenario. It can store it for that, but its more intention is, hey, I'm gonna store that today's afternoon's energy for tomorrow's morning. I'm not going to be used continuously for the whole night. Let that sink in. It's not designed for like, okay, overnight I'm going to provide power. It can do that. It's just inefficient for that. Its core focus is, I'm going to take the energy and I'm going to use that energy tomorrow morning. Your usage time would be just shifted. You are just offsetting it. So how they are storing the energy? They have very high pressure, basically water. So they are using pressurized water storage system, meaning they're going to have a pressure vessel like this going very hot water, like it has to be water. This is critical aspect. There is no steam here because again steam condenses, so volume will change. So you will have water at very high pressure, let's say 50 bars. The tank will literally store 50 bars of super hot water. Now what does that mean? That simply means in the morning when you need steam for cooking, you will have just a bleed valve, high temperature steam. It won't be like, oh, overnight it condensed, or now instead of super hot steam, you are getting hot water. No, you will get steam when you need it. Now, of course, this is currently under testing. It does work. It's a known science, but question is how efficient it is, how optimized it is. What is the pressure where it's like perfect without costing too much, because pressure vessels are expensive, especially if you have water there, because not only it's going to expand just out of pressure, it could like, if the chamber wall breaks, that water will turn into steam, expanding exponentially. That will cause immense amount of destruction. So for that reason, these things are tough. And again, you may be like, hey, more pressure equals more good. That's true engineering wise, but your cost is like, nah, bro, the tank becomes exponentially more expensive. So this is under testing. Like, we know how it works, is just optimizing it, cost optimizing it, is, use case optimizing it. That's what's going on right now. There is no salt involved, there is no magical oil involved, nothing like that. It's just high pressure, high temperature water. Then we come to the future aspect of it. So this is a great tool for hot places. Why? Because again, India do not invested too much into it, because we need cooling, we don't need heat. But here it works amazingly well, because even though India is hot, we still need a lot of steam for a lot of our industry. So in those sort of scenario, this is like, shut up, take money. And sun is cooking us. Why the heck India does not have so much server, even though we are like a super large user base? The problem is server will be, well, idiotically expensive because of our hot ambient. This takes care of that. Sun is like, I'm putting extra love. This is like, bro, I'm using your love to cool my CPUs. So this is super awesome. Basically using the heat directly to cool. And because it's amplifying the temperature so much, it actually works. That's the reason why you cannot just have solar water heater running your refrigerators. It can be done, but problem is the ambient gap. Basically, you barely is gonna get 80 degrees Celsius. Ambient in case of India could be as high as 45 degrees Celsius. Gap is not much. Here the gap could be idiotically high, 500 degrees Celsius versus ambient of 50 degrees Celsius. You see the gap? You need large amount of gap into your working fluid. For that only then your basically absorption chiller will work efficiently. Can you have a low temperature delta absorption chiller? Yes. Would it be very efficient? No. That's why we don't use it. But this bypasses that issue. By concentrating it, it's basically like a step-up transformer where it's increasing the voltage so it can be used more effectively. So it's super awesome for us. And enough electricity for all auxiliary units, that's also a big ass bonus, because these things are huge. They consume a lot of motor power just to move it. 2-axis tracking is not a big joke, and you have to understand it is designed to withstand winds. So there is some serious horsepower, serious oomph. This is Australian design. These are some small variant design. So all of these things require auxiliary power. Now, if you can get all your auxiliary needs out of, the bigger the better. This is way too small, but bigger the better. If you can get all the auxiliary power plus some surplus, that's like, shut up, take money. Imagine this, like, I have this, what does it do? It runs my air condition and gives me few kilowatts of power as a bonus. That's like, shut up, take money. Flat out. This actually unlocks the ability to, as long as you have good water supply, anywhere in India you can put basically servers, or even in desert area, if you have a closed loop steam system, you could even achieve that also, where it's like, hey, completely in desert, I'm using the sun. Again, you will have normal solar farm for electricity, this for cooling, and then done. You don't have to pay for heating or cooling, you don't have to pay for electricity, you're done, you're good. So it's a really good tool, and I'm really happy that this is happening in India. Somebody is like putting the pieces together in a very amazing way to get amazing results for us. So this was my presentation on world's largest solar concentrator dish. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.